Honestly, it really doesn't hurt.
It becomes an esophagus eventually, but esophagus.
Okay.
I know, but I can't eat it.
We're not.
I go Black Friday shopping.
You had to go Black Friday.
I was gonna see this puppy.
Did anybody go see Dana at Bath and Body?
I got some candles.
Black Friday? Oh, she was going to be there Black Friday, but I ended up going someplace else. Okay, so I think that thing up there is going to go away. Remember that the more highly substituted the double bond, the more stable it is. All those R groups are donating electron density into the double bond that helps stabilize it. Okay, here's tri, di, and mono. Okay, and of the di-substituted ones, the trans one is the more stable. It's more stable than the cis one. So I guess you could kind of put the cis one on that little list too. Okay. All right, here you go. Let's see where you are. That thing is not going away.
What?
What do you think of him? Guys, I'm like so scared. You know what luck I have.
I'm hungry. The force. Oh, hello.
That
I
help?
really need the force.
Yeah, cut the force off the.
I cut off the force? Oh my God, we can't have that.
I don't.
It's what reagents would be
Be
the
the
best.
best.
Okay, so here's where you're starting, here's where you're ending. What should you use up there? A, B, C, D, or E? I'm hoping that thing's gonna go. Usually that thing goes away. It like goes up. I'm scared. Does that mean it's not working?
Hey, what's the
green box
What's
is
the
around.
channel name?
Yeah, and that's like a good sign.
Right? Okay, thanks.
What? The channel? 41. It's okay. All right, so I got a couple more. All right.
No, the doors.
Oh, I got like nobody picked D.
Okay, but we're too poor for clicker points. Can't afford it.
Yeah, I hear you. I hear you. Okay. This is the correct answer.
Oh, it's right.
So now we're going to talk about which one's a why. Okay, why it is. Okay, so what are we doing? What's the difference between the starting material and the product? We made an alkene. Okay, what else? Which hydrogen? We lost a hydrogen from here and a bromine. So this is minus HBr. Okay, so what do you use to lose an acid? You have to use a base. Yeah. Okay, so that cuts out. Right? Okay. What about methanol? That can function as a base, but look at the other ones. What's the base in A? What's the base in B? Okay, so they're negatives, so they're going to be stronger bases than C. Now, how do you decide between A and B? Yeah, because if you used A, I'll just write it like that. This is what you would get. What's the difference in those bases in A and B? B is what kind of base? What? What? Bulky base. If it's a bulky base, it will take the easiest proton to get to, which is one of these on the end. Okay?
This is a tomato. Think it's good for you? My name is.
Just ruined my whole thing. Tomatoes.
Because you know I'm all about that base, no acid. All about that base, no acid. All about that base, no acid. All about that base, base. Yeah, it's pretty clear. I ain't no science fool, so you got litmus. Well, I can turn it blue, make it go boom boom all over the place. When all the H plus meet all the OHs, pink phenolphthalein, I think that's straight dope. Mix in a little bit here and it'll make it so. You want it neutral, pH is low. Better set up a titration with a strong hydroxyl drop. And my left ex, she told me don't worry about your eyes. If an acid gets in, then we just have to neutralize. You know I love me, my stomach, and all the things it dissolves. But my mouth that keeps it from eating my intestine walls. Because you know I'm all about that base, no acid. All about that base, no acid. All about that base, no acid. I'm all about that base,
No, I didn't know because she was like in the one on the left. I was kidding.
Stoichiometry, yeah, that's where it's at. And it'll tell you. Yeah, my left ex, she told me don't worry about your eyes. Cause if acid gets in, we can fix it without the lie. That we know I love me, my stomach, and all the things it dissolves. But my bowel that keeps it from eating my intestine walls. Because you know I'm all about that base, no acid. I'm all about that base, no acid. I'm all about that base,
This was my idea.
all about that base, because you know I'm all about that base.
I said you move your shoulders. And then the video came out and I was like, oh my God.
All about that base, no acid. All about that base,
I couldn't made that video.
How are there 700
I don't know. Maybe they didn't get it. I can't even get
Hey,
that to
musical
go
scientists, welcome to my second channel.
Hello.
Did you survive? Okay, it's all about that base. Okay, so if you're removing acid, you use base. How do you know if it has to be bulky? It's on the end.
Okay, can you repeat that? Why do I know it's bulky, or how do I know that?
How do you know it's bulky? Because you have this big group.
How do I know I need to use a bulky?
Because the double bond is on the end and not in the middle.
Okay.
Ooh.
Thank you.
Wow. That's crazy. Is that thing going to be blocking it the whole time? All right, it says rates of dehydrohalogenation at the top. Do you have that part on your slide anyway? On your printout, okay. Okay, just like substitution, the better leading group helps. So iodides are faster than bromides and chlorides and fluorides. Okay. The other thing is tertiary alkyl halides are the fastest because you form the more stable double bond. Okay. So the reason is different than why it's the fastest in an SN1 reaction. In an SN1 reaction, tertiary is fastest because you're making the more stable carbocation. But here, we aren't making a carbocation. This is E2. We are forming the more stable alkene. Okay? And tertiary and SN2, no SN2 on tertiary centers, right? Write that down again. Can I go back? What are you writing down?
Everything on there besides the arrow.
Yep.
Oh. We'll just write tertiary, secondary, primary. Okay, now, in this reaction, we have a tertiary alkyl halide, right? And we're adding water. Okay, you can actually make a double bond. Okay, but is water a strong base?
No.
No. Good. Okay, in this reaction, they found the rate is only dependent on concentration of the alkyl halide. So it's first order. Our E2 reactions, the concentration of the base made a difference. Here it doesn't make a difference. This is elimination unimolecular. What does unimolecular mean? One molecule present in the rate determining step. Good old E1. Okay. All right, we're going to do it. You ready? So here's our starting material. We're going to add, maybe, if I can get something, water to it. Okay, and what's going to happen? Okay, well, this is a weak base, and we have a tertiary alkyl halide. So what will happen? Just like the SN1 reaction, the alkyl halide will leave, and what are we going to make? Here's what didn't change. Okay, now what changed? What happened to the bromine? It did. And how many lone pairs does it have? 4 and a negative charge. What else do I need? What happened to that carbon right there? Positive. Are you positive? Okay, now here's where we're going. Right down there. Okay? So what will happen next? Here, we'll be very festive and use green. What? The oxygen of the water is going to do what? It's going to pull off a proton. Those electrons are going to go down there to make the double bond. So here's our new double bond. Okay, what else did we make? What happened to the water? Yes. What is that called? Yeah, hydronium. Okay. Whoa. We're going to draw the reaction coordinate diagram. So how many steps do we have? 2. So how many mountains are we going to have? 2. So which one is the tallest? The first one or the second one?
First.
Why?
Because it's E1.
Because that step is the rate determining step. So here I am at the top. Tell me when to stop going down. Are you going to tell me?
Right there's about
Y'all are hilarious. Okay, what's under here? What is this? This is a what?
good.
The what? A valley. Yeah, what's in the valley? Who? The intermediate, which is our little carbocation. Okay, what's at the top? Okay. Okay, we're going to draw those transition states, but I gave you a whole slide to do it, I believe. Did I not? Hmm? All right, so transition state 1. What's happening in that step? Okay, that's where our molecule we started with, and what did it do in the first step? We took the electrons and put them on the bromine. Okay, so okay, this bond is breaking. All right, that didn't work very well. That was my plan. I'll try to put another little one up there. Okay, that bond is breaking. Okay, that's your transition state. Now, what about charges? Okay, and what charge? Yes, because positive character is building up in the transition state. What about the bromine? Because it ends up negative at the end. So negative charge is building up in that. Okay, now how about the next one? Okay, so we have, and it does not matter which hydrogen you would pick, by the way. If you pick the one on the right, it works just as well. Okay, so what are we doing in this step? We have water, and what is it doing? It's making a bond to the hydrogen, right? Okay, what's happening to the HC bond over there? It's breaking. Okay, so we have a partial bond there. And then what's happening between the two carbons? We're making a double bond. Making that bond, breaking that bond, and making that bond. Okay, that's all happening in that step. Okay, now what about my charges? Who gets what? The O on water gets a, right, because it ends up positive. What about anybody else? This carbon was positive to start, and at the end of the step, it's neutral, so it's losing positive charge. Okay, so that's your second one. You only have as many transition states as there are steps. Don't try to make extras. All right, does that make sense? Are you getting how to figure these out? Because it'll be helpful if you just get that process down. We're not going to draw like everyone ever. Okay, in an E1 mechanisms, guess what? The iodides are the fastest. You notice a little theme there? They're always the fastest. because it's a good leaving group, whether you're substituting or eliminating. Okay, now down here, benzylic, do you remember what that was? Next to a, we'll write it up here, next to a benzene ring. That's benzylic. What's allylic? Next to a double bond. Not on the double bond, next to the double bond. I think I do better with my fingers, seriously. Okay, so why are those as fast as tertiary? Why are those? Right, what makes them more stable? Resonance. You can do resonance with those. Okay, vinyl, do you remember what that one was? That is on a double bond, okay? We don't make carbocations that are on the double bond, okay? They're not stable at all. Okie dokie. Okay. The major product in an E1 reaction is still the most stable alkene. All that's different is how you get there. Okay, which path you took. If you have a strong base, it's going to be E2. Okay. If you have a weak base, you can get some E1. Okay. We did E1 in a different reaction too, which was what? We dehydrated alcohols, and that was in E1, okay? All right, so what do you think would happen in this one? We're gonna make a what? I couldn't hear you, like.
Oh, I said we're gonna take off the chlorine.
Take off a chlorine and a hydrogen. Okay, what happens when you take off the chlorine? What do you get? Oh! When you take, is that still not it?
There you go.
Well, I really messed it up. Okay, so you're gonna get okay, any ideas? What kind of carbocation is that? Somebody said it. Be brave. Okay, so what will happen? What do you think is going to happen? There's going to be what?
A shift.
Yes. What will move?
Yeah.
A methyl. Why does it want to do that? Because what will we get? What is that? It's tertiary and it's what? It's next to a, what is this? A benzene ring. It's tertiary and benzylic. It's like super stable. Okay, then what do you think the methanol will do? What proton do you think it's going to take? Which one? Yep. So you're going to get that. Yeah, we got that? I could try to draw that step. I kind of mangled the molecule by writing in it. All right, let me get another color. Maybe that will help too. So we're going to pull off that proton, and those electrons are going to go there. Get this. Okay, so anytime you make a carbocation, you got to look for rearrangements. Okay, you got to check. That'll mess you up if you don't. Okay, now when you do this reaction, okay, this is an E2 reaction. We didn't talk about the stereochemistry much. But when you do this reaction, the KOET and ethanol, do you notice that this is symmetrical? Okay, so your base is going to pull off a proton on either side. It doesn't matter which one because it's symmetrical. If it wasn't, if there was only two, you just get mixtures. Okay. Okay, the ratio is going to be 77 to 23. Okay, so do you remember why? Remember I showed you the Newman projections? Okay. So if you have okay, when you pull off the H that's anti to the leading group. Okay, and when the R's are on the opposite sides, that one is more stable because the R's are anti to each other. Remember, you can rotate around single bonds. Oh, well, maybe you don't remember. Okay. Remember, though, that when you do a ring, you get the cis double bond, right? Because that's the only way they can hold hands back there. They can't be spread. They won't meet each other. Okay, so one of the ways that they used to figure that out was they did this little study. That's a bromine at the top of that molecule. Do you have the little molecules on your slide?
What was in the little bowl?
Just that more stable trans, except in rings it was cis. Okay. Okay, so here is a molecule, and look what they did to this chair. They put on it this group, which is one of the bulky T-butyl groups. Okay, one of the bulky T-butyl groups. Okay, T-butyl groups, do they want to be equatorial or axial? T-butyl groups. Equatorial, because you're avoiding those 1,3 diaxial interactions. Remember, everything comes back to haunt you. You can't ignore it. Wait till next semester when all this semester comes back. Okay, so because of that, remember I showed you two chairs with just a T-butyl group on, and I showed it to you equatorial and I showed it to you axial. It was 99.99% equatorial because the T-butyl group was so big, okay? So by putting that on the chair, what happened is they stuck it in this position. Okay, so the bromine up here that is being blocked by the weird deal, the bromine up there is what kind? Axial. Okay, where are the hydrogens that are anti to that bromine? That would be this one and this one on either side. The thing is symmetrical, right? Okay, so this compound is cis, right? Because the T-butyl is up and the bromine is up. That reacts super fast, okay? Because it's locked where the hydrogens and the bromine are anti to each other. And so the base can go zoom, 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 and it does it really fast, okay? Over here, this is the trans one. The bromine is equatorial. Notice the T-butyl group is still equatorial, okay? But what is anti to the bromine now? It's the carbon, this carbon, okay? Remember that you're looking down the bond. Okay, so here's your bromine. Oh, this is the rest of the molecule. This is the rest of the molecule. So there isn't a hydrogen that's anti. Only 0.01% is anti. So what will happen is that 0.01% that isn't stuck like that will do the reaction, and then a little bit will shift the equilibrium, and it takes forever. Okay, so that's why this one is 500 times faster than the train. Okay, because this is axial to that. Okay, does that make sense? You see that the hydrogens are axial to the bromine. Okay, because that's real important. What was that called, that arrangement? There was a term for it, anti-periplanar. Remember that? Anti-periplanar or anti-coplanar. Okay. Okay, now, whenever we do reactions with alkyl halides, there is a competition going on between substitution and elimination. Okay, they can both occur. Which one is major is the question. Is it going to be substitution or is it going to be elimination? Okay, number one, look at the structure of your alkyl halide. Is it primary, secondary, tertiary, or maybe benzylic or allylic, which would favor carbocation formation? Okay, so primary alkyl halide, you're going to get mainly substitution. If you have a secondary, you can get both. Okay, and if you have tertiary, you can only get elimination. No SN2 on tertiary centers. When you're looking at SN2, you're going to have something negative. You're going to have a negative nucleophile / base. Okay, so like O ET minus is a strong base. It's also a strong nucleophile because it's negative. Okay? So there are some things you can do to try to keep that if you want substitution to be your major product. Number one, use a polar aprotic solvent. That will really help substitution. Okay. So what's a polar aprotic solvent? Can you name me one? How about that? DMSO. Give me another one. DMSO is dimethyl sulfoxide. DMF is dimethylformamide. Acetone's another one. What is the deal with polar aprotic solvents? Why do they help substitution? Because they are solvating what? They're solvating one thing and not solvating the other. Solvating is where the solvent molecules stabilize stuff. That's why things break into ions, because the solvent is stabilizing it. You just have salt sitting on your counter, it's NaCl. It's not salt, sodium ions and chloride ions that are separated. They're right by each other. But when you dissolve it in water, they separate out because the water molecules are surrounding the sodium. They're surrounding the chloride. Okay, and I'm sure in journal chemistry they went into horrible detail on that. Like, did you have to figure out the lattice energy? Yeah, I remember doing that. No fun. All right, so all you have to know is it's polar, and what is the aprotic part? Does not have a hydrogen available for hydrogen bonding. That's why water is not a polar aprotic solvent. Water's polar, but it's polar protic. It has hydrogens available for hydrogen bonding. So it will stabilize things that are negative and things that are positive. It will stabilize both sides. So if you can't stabilize things that are negative, it makes them more reactive. The term we used for that was naked nucleophile. Okay, because it didn't have solvent molecules, so it went zoom right in. Why is my phone? Beaumont, Texas. Okay, SN1 versus E1. Look at primary alkyl halides. What does it say? Neither SN1 nor E1. Okay, but you should look for rearrangements. If you have a primary alkyl halide that could rearrange to a tertiary one, then yeah, you gotta look for it. Secondary alkyl halides and tertiary alkyl halides, you can get total mixtures. Okay, so what again you're going to have to do is look at your nucleophiles. Okay, a tip for you is that pretty much substitution is favored when you have a weak base. Okay. You can remember you're going to get both. Which one is major is going to be determined by whether your bases are stronger or weaker. Okay, it's all about that base, Okay, substitution is favored when there is, we're going to do a buttload of examples here in a minute, is going to be favored when there is decreased crowding at the carbon with the leaving group. Exception, bulky base will still favor elimination. So what's your bulky base? Potassium T-butoxide. Because now that would have been the nucleophile, and it's not going to want to be a nucleophile. Okay, as you lower the basicity of the nucleophile, it favors substitution. Okay, tertiary alkyl halides always favor elimination with anionic nucleophiles. Only in solvolysis does substitution predominate. Okay, so what is solvolysis? When the solvent is the nucleophile, like methanol, water, ethanol. Okay, and then it's SN1, y'all. It's not no SN2 on tertiary centers. No SN2 on tertiary centers. All right, so here is the temperature factor. I don't know why that's up there. As the temperature goes up, the rates of both substitution and elimination increase. Does that make sense? You heat it up, it goes faster. Okay? But the rate of elimination increases faster than substitution. So if you want substitution to be major, what you can do is cool it down. If you want elimination to be major, you can heat it up. If you're separating a 90-10 versus a 70-30 ratio, you're going to get more stuff from the 90-10, if that's what it is to begin with. So a lot of times we alter the conditions to allow one to be favored over the other. Heat will favor elimination. Okay? At higher temperatures, the proportion of elimination to substitution is greater. Okay? Okay, now I think we're there. All right, so here is a starting material. Okay? Isopropyl bromide, and we are adding NaOCH2CH3, sodium methoxide, in ethanol at 55 degrees. Okay? Now, a way to approach these kind of problems where you have to come up with the major product is to draw out both the substitution product and the elimination product, and then that often helps you to decide. Okay, so what is the substitution product for this reaction? And they're both formed, but one is going to be formed more than the other. Okay, so what's the substitution product? What's your nucleophile slash base? What is that? What's the thing we're gonna, okay, what's the leaving group? All right, we'll start with that. Okay, so what would substitute for the bromine? Sodium? What is it? I've seen everything on the test. You got to be able to pick them out. Okay, so what would be your substitution product? In place the bromine, we would put what? OET, right? Okay, what is elimination product? What hydrogen would be pulled off? One from the methyls, right? Okay, so those are your two. Okay. Everybody see how we got substitution product and elimination product? Elim. We're just going to write elim. Okay. Now, how do you decide which one is major? Well, what is the structure of our alkyl halide? Is it primary, secondary, tertiary? It was what? Secondary. Oh, dang, because that one's the one in the middle, right? Okay. We have a good base, though, don't we? It's also a good nucleophile, but we have a good base. And what can you tell me about the temperature? What's room temperature? It's what? Yeah, 25 is a good number to remember. Okay, 25 is around room temperature. Okay, so is this above room temperature or below? It's above. Okay, so which one do you think is major? Elimination. Okay, this is the ratios. It was 13 to 87. Okay, so this one is major. Now, what mechanism do you think it was formed by? E2, E1, SN2, or SN1? The major product. What do you think? Okay, first of all, if these were your multiple choice and these were your 4 choices, what could you rule out? Thank you. Okay, now what favors E2? Strong base, good leaving group. What favors E1? You have to be able to make a stable carbocation and weak base. Okay, so guess which one it is? E2. All that to get that. All right, we're going to do it again. All right, look at this one. Okay, so what are the substitution and what are the elimination products? Okay, what's the leaving group? Br. Are you sure?
Yes.
Because y'all were not saying that. Okay, what is our nucleophile slash base? Okay. So what is the substitution product? Instead of the Br, we have the OET. What's our elimination product going to be? Bless you. What's our elimination product going to be? Which one do you think is major? Make your bets. Place your bets. What changed? Okay. This is what kind of alkyl halide? Primary. If you wanted to get, let me get something else to write with. If you wanted this to be major, you could do it, but you have to change something. What would you change? What? Bulky base. Perfect. If you use this base, this would be major. Okay, now, what was the mechanism, you think? Okay, that for the major product. Okay, this is our major one. Let me go back to red because I don't want it to look like I was talking about that other one. What is the mechanism for the major product now? The original question. Yes. Okay. It's primary. You're not going to make a stable carbocation. So it's SN2. Okay. Do you see why it's not E2 or E1? Because we're not eliminating. Okay. If it was the green reaction up there, what is it going to be? E what? E2, it's primary. Okay? How do you feel about that? That's like the hardest part of the whole deal is this, figuring it out. We worked all the week to get there. All right, I will see you Wednesday morning.